Hello students, welcome to today's session of chemistry. As you all know, we have started with 8th lesson of your syllabus, that is transition and inner transition elements. We call them D block elements and F block elements. Out of these two types, we finished study of transition elements and we started with inner transition elements, that is F block elements. As I told you earlier also that inner transition elements or F block elements are in the D block itself. But as they are not accommodated there and according to electronic configuration, they are placed separately in F block, and F block is located at the bottom of the periodic table. So there are two horizontal rows consisting of 14 elements each, and those are called inner transition elements. Inner transition elements contain lanthanides as the upper row and the lower row as actinoids. We have learned in detail about lanthanides as well as actinoids. And today we are in the last session of this lesson. Now few points are remaining which we will cover in this session. So let us start with study of some similarities and differences between lanthanides and actinoids. So let us study what are the similarities in lanthanides and actinoids. Now, both are F block elements. One, that is lanthanides, we say, is located in third group and sixth period, while actinoids are located in the third group but in the seventh period. Both contain 14 elements each because F subshell has a capacity to accommodate 14 electrons. So F subshell starts filling up, and when it ends, that block also ends. Now, because of the similar last shell electrons, they must have similar properties. But there are some differences as well. So separately we'll study similarities and differences in lanthanides and actinides. So let us start with similarities. Both the series, lanthanides as well as actinides, they show +3 oxidation state. In both the series, as they are a block element, the f orbitals are filled gradually. In both the cases, ionic radius of the elements decreases with increase in atomic number. In both the series. The electronegativity of all the elements in both the series is low and they are said to be highly reactive. Why this is so? Because in the periodic table, if you see, their location is near to S block elements than that of transition elements. They behave chemically similar to S block elements. And what are S block elements? They are alkali metals and alkaline earth metals. So, both of them have very less electronegativity. Like that, lanthanides as well as actinides also have less electronegativity and they are highly reactive as that of S block elements. The nitrates, perchlorates and sulfates of all the elements of lanthanides as well as actinides, they are soluble. But the hydroxides, fluorides and carbonates of them are insoluble in water. Understood? So these are the similarities between lanthanoids and actinoids. Now, what are the differences between these two? A separate question may be asked. What are the similarities? Or sometimes what are the differences? So, differences we will study. First one, lanthanides show a maximum oxidation state of +4. General oxidation state in both the cases, in both lanthanides as well as actinides, is +3. But some of the elements of lanthanides as well as actinides show variable oxidation states. And if you compare between them, then lanthanides show maximum of +4 oxidation state. But actinides show oxidation state of +4, +5, +6 and +7 along with +3. That means highest oxidation state shown by actinoids is +7. Now, second one. Lanthanides do not form complexes easily. We have seen in detail that coordination compound formation tendency is of actinoids. So actinoids have greater tendency to form complexes with ligands. So ligand gets attached to the central metal atom and they form a complex compound. And this tendency is more in actinoids than lanthanoids. All lanthanoids are non-radioactive except promethium, but actinides are radioactive in nature. Now, if we look at the periodic table, atomic number 82, that is lead. After lead, all the elements are radioactive, as lanthanides are in between. Atomic number 58 to 72, they are not radioactive. But actinides are between atomic number 90 to 103, that is above lead, above 82. Hence, all actinoids are radioactive. And lanthanides, in lanthanides, only promethium is radioactive. Lanthanides do not form oxocations. Oxo, that is oxygen. Cations, that is positively charged ion. So, lanthanides do not form oxocations, but actinides form oxocations. Like uranium forms UO plus, uranium oxide. Like plutonium forms PuO plus, and neptunium forms NPO2 plus, that is cation. So, actinides have a tendency to form oxocations. Now, if we compare about the color of the elements, then lanthanides, most of them are colorless, while actinides are colored ions. So, these are the similarities and differences between lanthanides and actinoids. So, go through them because sometimes a question may be asked like that. Now, we will study next point as postactinoid elements. As the name suggests, post is after. Actinoid, postactinoid together means after actinoid elements. Now, where does the actinoid elements end? At 103 Lorentz. But if the periodic table, if it is complete, then the last member will be of atomic number 118. That means from 104 to 118, the elements are called post-actinoid elements. In earlier days, the elements after uranium are called transuranium. Nowadays also those are called. So the elements after uranium, that is atomic number 92, are called transuranium. So between 93 to 103 are actinoids, but after 103, that is 104 to 118, they are called postactinoid. So from 92 to 118, together they are called transuranium, and of transuranium elements, 93 to 103 are actinoid, while 104 to 118 are postactinoid. Understood? So these are postactinoid elements. As we have completed almost study of all the periodic table, the only elements remaining are from atomic number 104 to 118. Where they are located in the periodic table? They are the transition elements itself, because D block itself has a block elements. Then after a block, the elements are there in the transition element, those are we call transition metals. The postactinide elements that are known so far are transition metals. They are included as postactinoids because, similar to actinoid elements, they can be synthesized in the nuclear reactions. As I have told you, all the actinoids are radioactive, or we can say after lead all the elements are radioactive. Now, Many of the radioactive elements are synthesized in the laboratory. Because of their very short half lives, they don't exist in nature. Hence, they are synthesized by the nuclear reactions. Now, so far, 9 postactinoid elements have been synthesized, and it is difficult to study their chemistry owing their short half lives. Now, as I told you, 103 to 118. That means almost all periodic table, if it is complete, if we are able to prepare all the elements after or post-actinic element, then it will be up to 118. But so far, we are able to synthesize only 9 post-actinoid elements. That is up to 113. And hence, 9 post-actinoid elements in total are available. But still, this study is very difficult because after preparation also, they live for very short period. That means their half lives are very short. Out of these elements, Rutherfordium, so this is the name after the scientist Rutherford. Rutherfordium forms a chloride, RfCl4, that is Rutherfordium tetrachloride, similar to zirconium and hafnium in the plus 4 oxidation state. RfCl4, that means Rf has plus 4 oxidation state. So, of 9 postactinoid elements, Rutherfordium, zirconium, and hafnium form a chloride with oxidation state plus 4. Of postactinoid elements, dubnium, that is Db, that is similar to both group 5 transition metals, which are those niobium and actinoid, protactinium. Both are V, that means they are showing 5 oxidation state. So in post-actinide, dubnium resembles two transition metals, that is niobium and proactinium. Understood? So this is all about post-actinoid elements. Now almost everything is over as we have studied all the transition as well as inner transition elements. Now we will compare or we'll study some comparison points between what pre-transition, lanthanoids and transition metal. What are pre-transition metals? That means S block and P block elements. What are transition metals? That are D block elements. And what are lanthanides? We know them. That is inner transition elements. So we will compare between pre-transition, transition, and inner transition, that is lanthanoids. So this is the table. We will see one by one. So first column belongs to pre-transition metals. Second is lanthanides and third is transition metals. So first point, if we compare the oxidation states in all of them, so generally pre-transition metals, that means metals in S and P block, they show N plus oxidation state. N plus N is the nth shell, last shell. So generally they are monovalent, essentially monovalent. But lanthanides, we have studied them, they show plus 3 oxidation state, which is common, and sometimes plus 4, plus 2, etc. But transition metals, they show variable oxidation state from plus 3, plus 4, plus 5 to plus 7. Now, second point, if we compare periodic trends, those are shown by S and P block elements, they are because of the effective nuclear charge. Effective nuclear charge. That means if we compare the atomic size and the atomic charge, together it becomes effective nuclear charge. While lanthanides, they show periodic train, in yet they show lanthanoid contraction. And transition metals, that is d block elements, their size changes like m raised to plus n. Transition metals also show variable oxidation states. So they show in periodic trains their size changes, and because of that they show variable periodic trains. Pre-transition metals, if we see S block elements and P block elements, all the elements in single group, they show similar properties. Lanthanides, as the name suggests, they all are almost similar in their properties. But transition metals show some variation in their property. That means in a group, if we compare all the elements of D block, they don't have similar properties, they change. Pre-transition metals are hard enough. Lanthanides, they are not so hard. Here there is one mistake, and that is in textbook also. Hence I have taken that. Always hard it is written, but actually lanthanides are not that hard enough. They are soft. So textbook also make a change. That's why I have taken like that only. In transition metals, heavier metals like iron, copper, they are somewhat soft because of, again, there are so many unpaired electrons, hence they are somewhat soft. Pre-transition metals, lanthanides and transition metals, if we compare, ligand field effect are at most in transition metals, but they are not so significant. In pre-transition they are almost absent, and lanthanides they are not significant. And like that, coordination complex formation or coordination number 6, that is maximum, is observed in transition metals, and which is not in pre-transition metals. But lanthanides, because a block has number one paired electrons, they show high coordination number. In geometrials, if we compare, so flexibility is observed in pre-transition metals and lanthanides, while transition metals have fixed geometry. And magnetism, that is paramagnetism, diamagnetism, these properties, those are shown by lanthanides as well as transition metals, but those are not shown by pre-transition, that is S and P block. So this is all about transition metals and inner transition elements. So here ends your lesson. I have almost finished or completed all the syllabus which is there for this year board exams. Some of the syllabus has been reduced for your, or you can say, February 21 exam, so that I have not taken in this chapter only. Now, some revision, or let us look at the periodic table so that you will better understand the transition and inner transition elements. If we look at the periodic table, this is the best arrangement, we can say, or accurate arrangements of elements given by Mendeleev. So, in this periodic table, if you see, there are two groups. First two groups, they are S block elements. P block elements are to the extreme right of the periodic table, contain 6 groups, while D block elements are in between S and P block, which have 10 groups, and F block elements are there in the periodic table in the third group itself, and Lanthanides and Actinides, two series of 14 elements in third group and sixth as well as seventh period. So if you see at the periodic table, you will observe that to the extreme left, S block, that means strong metals are there, Metallic property goes on reducing as we move from left to right. And in P block, if you see, there are all the variety of elements. That means 18th group belongs to noble gases, 17th group halogens, which are all non-metals. This blue portion at the corner, these are non-metals. This last column is noble gases, and this zigzag line indicates metalloids, but all remaining all are metals, that is total S block, total D block, F block, and this portion of P block are metals. So periodic table is dominated by metals, we can say. And non-metals, about 10 non-metals are there. 10 to 11 we can say. Some are radioactive, so we don't consider them. And only 7 are noble gases, out of which 6 are known. So, total periodic table, if you consider, so metallic property is dominating. Out of that, after lead 82, all the elements are radioactive, hence they are very short lived, but out of them also, few elements have very, very long half life and which can be studied in detail and which are actually very useful in many aspects. So, in the 11th standard, we learn S block elements in detail and 3 groups of P block. And in 12th standard, we learned just of, I have finished, that is transition elements and pre-transition element, inner transition element, sorry. That means D block and F block complete. And the remaining 3 groups of P block that we have studied earlier, that is elements of group 16, 17 and 18. That chapter I have finished, and then I have started with 8th lesson, that is transition and inner transition. So in short, we learned all the periodic table along its physical properties of all the elements, their chemical properties and their applications, everything about these elements. When we see why that element is located in the particular group or in the particular block, then we came to know that the important base of this arrangement of elements is electronic configuration. So arrangement is based on electronic configuration, and electronic configuration is based on atomic number, that is number of protons, and number of electrons are same to proton. That means atomic number is very important as far as chemical and physical properties of any element if we want to understand. So, atomic number, we can say, is the identity of that element that decides all the chemical properties of that element. So, this arrangement in 4 blocks S, P, D, and F is based on the electronic configuration, that is on the atomic number. If you have any doubt when you listen to the videos, then please feel free and send your doubts on my personal number. Now, today's assignment: write a note on postactinoid elements and write similarities and differences between lanthanides and actinoids. So, we have finished this lesson also. So, I'm going to start with another lesson in the next session. Thank you.